the talk is structured as follows. We'll go through each of them as brief as possible. So the aim of the project is quite simple. It is to set up a Coma cluster configuration in Milgram gravity, MOND, to set up ultra-diffuse galaxies in MOND, and then to launch these ultra-diffuse galaxies into the Coma cluster on different orbits from different distances. Then we just study the evolution and stability of these UDG and compare them with what we have in the observations. Now, one might ask, why is this important? It's important, as Jonathan mentioned earlier, given the low internal acceleration of these galaxies, it makes them ideal testing grounds for the EFE. And Freundlich et al. Noted a tension between the predictions and observations, mostly meaning that the velocity dispersions of the observed galaxy are much higher than MOND predicts, including the EFE, particularly because the UDGs are quite close to the cluster center where EFE is significant, and there is a tension between the prediction and observation. These simulations that I'm going to show you also help us to see what we can study, what we can understand about the EFE, and of course there are other factors at play like tidal heating, etc. So I'll just do a small recap. So Jonathan, in Freundlich et al. They discussed possible first infall, heated or disrupted by tides, baryonic dark matter, higher stellar masses, MOND, modified inertia, screening of the EFE. What are the questions that we are trying to address? We are mostly going to check about first infall onto the cluster. Is it possible? Heated or disrupted by tides. We are going to check that too. So here the tools that we used was Phantom of Ramses for the simulations and extract POR for extracting the data. If one needs to look at how this works and where the algorithms are, you can follow it. You can find it in this website. There is also a manual for disk galaxy simulations in MOND. Now, initial setup is that we first use the cumulative mass profile of the Coma cluster given by Sanders et al. 2003, and then we use this mass profile to numerically invert it, convert it into a distribution function, and then sample particles from this distribution function and distribute them in spherical symmetry. So the yellow line that you see here is the theoretical cumulative mass profile, and the dashed line that you see here is the cumulative mass profile of the cluster that we have set up in MOND. So my friend, Jonathan explained how the mass profile is done, so I won't go deep into that. But what I want to point is the cluster that we have set up matches the theoretical profile very well. So that's good news. Now the UDG we set up have a solar mass of 1E7 and Essersic index of 1.0 and effective radius of 1.5 kiloparsec. Like, why did we choose that value? Simply, it's just an average of what we have in the Yagi catalog that was used by Jonathan Freundlich et al. So I just took an average of those values as a first trial, and now we are to place this UDG inside the cluster, but the cluster has external field effect, so we have to place them in equilibrium with the external field effect. So we use this formula for acceleration, and then we set up Sérsic spheres with the following parameters such that they are in equilibrium at the location they are placed in, and then we launch them on different orbits. The simulations, all of them are run for 5 giga a year. These are the velocity dispersions that are set up from the UDGs. So this is the Newtonian one, this is the MOND one, isolated MOND one. The remaining one are the ones after taking EFE into account. So yeah, these are the dispersion profiles of the simulations too. So just to summarize what I have, what I set up in a single picture, all these we will consider them UDGs placed. This is the Coma cluster image actually, and the center. So we place them 1 megaparsec to 1.24682 megaparsec, and then these are different eccentricities: 0, 0.2, 0.4, 0.6, 0.99. This is the enclosed mass inside each of this radius, and this is the circular velocity at these radii. We also do 3 auxiliary simulations just to check, and we launch them on highest eccentric orbit, 0.99, just to check whether if we launch them from very far away, will they be able to show us will they show a different behavior? Where, so this is how simulations are set up. We launch them for 5 giga-years, we run them for 5 giga-years, and we have some results that I would like to share. So we'll go through one by one. Tidal susceptibility. Firstly, we have to, this is not a result, but rather a factor that we have to consider is that this is the tidal susceptibility for the UDG that we are using, and at 1 megaparsec the tidal susceptibility is quite high. Actually, for all the distances, there is some tidal susceptibility. It's just that if this has to go to 0, we have to be away. More than 10 megaparsec away from the cluster. So all these simulations are already been placed in a tidally susceptible environment. These are relatively less susceptible, but still they are not close to isolated MOND, as I will show you. So the tidal susceptibility is calculated using this equation, half mass radius by tidal radius. The detailed calculation is in Appendix B of Freundlich et al. Just to emphasize that they are already in a tidal susceptible environment. This is what I am plotting here is mass fraction at each snapshot divided by the mass fraction inside the initial divided by the mass inside the initial tidal radii. So I use the tidal radii at the initial distances, and at each snapshot we calculate what's the mass inside this tidal radii. We plot them as a function of time for the simulations. So what you see here are for the low eccentric orbits. Most of the simulations, they don't lose too much mass within 5 giga-year, but the ones that I place at 1 megaparsec from the center, they lose mass in all eccentricities. So as the eccentricities increase, there is significant mass loss. And for the highest eccentric orbits, almost all simulations lose more than 80-90% of their initial mass. Now, what is this solid black line? This is just a criteria for us to get a better idea. I consider this as a disruption criteria when the UDGs are undergoing disruption. So if the mass fraction goes below 20%, then we consider the UDGs to be significantly disrupted or undergoing disruption. Eccentricity plays a very important role in these simulations. So once we have all the plots, once we have all the data, we generate images and feed it to Galfit. We give it to Galfit, and from Galfit we get Sersic index, aspect ratio, effective radii, and I think position angle. So we get four parameters as our fits, and we take the Sersic index here and plot it for. We have done 36 simulations or 39. I'm just showing the extreme cases what we have. So this is the most stable case one where the Sersic index does not change much. It remains constant, almost constant. At 1 megaparsec, this should be stable, but because of high tidal disruption, after some point, the Sersic index changes a lot. The dashed line is where I say, well, it's lost more than 80% of its mass. Same goes for here. But this is highly eccentric orbit, so it loses mass very quickly, and the Sersic index vary a lot. With the same goes for 2 megaparsec with highly eccentric orbit. Now, what is the color bar? One may ask. The color bar is m sigma relation. We use sigma to the power of 4 by initial mass inside initial tidal radius, and then the upper limit is isolated MOND. The lower limit is for isolated Newton. So our galaxies roughly are above Newtonian regime, but they don't hit complete isolated MOND regime. They go high, but I will show you how it goes, how the velocity dispersion goes. But after a point, the Sersic indexes are unreliable. For example, this line here, Galfit does not fit anymore, it just gives errors, so you cannot trust those fits after this point here. Same, we try to plot the aspect ratios too. Again, same pattern, that stable orbits, you get stable results. For unstable orbits or highly tidal susceptible orbits, you get this like weird, I don't know if it is weird, but it's very varying a lot. And at some point, again, an interesting trend is that after, when I consider disruption, the dispersion goes to a higher value. Now, how high is the question. This is aspect ratio calculated from inertia tensor. For inertia tensor, this is just for our information here. But yeah, this is just for our information. This is where I think this is the pericentric passage. So after pericenter, the values just drop. The values just drop and it changes a lot. We have to interpret what this means exactly. Now, this is the most important result that I wanted to present, is that this is the line of sight velocity dispersion of the, so firstly, all these galaxies, when we launch them into the Coma cluster, we can only catch them at their apocenters. So we are most likely to catch them at their apocenters. So I use all the snapshots where the UDGs are at the apocenter, and then I take the we take the line of sight velocity dispersion for these snapshots divided by the isolated MOND prediction for that galaxy at that snapshot, meaning I use the mass, effective radii, and Sirsic index for that particular snapshot, and use the isolated MOND prediction at that particular apocenter. This is the one line. So for low eccentric orbits, the velocity dispersions don't reach the isolated MOND limit at all. Here also. Only the dashed line, meaning they are under disruption, they are under disruption. So at low eccentric orbits, they cannot reach the isolated MOND value. For higher eccentric orbits, however, some of them seem to reach isolated MOND prediction, especially for this case. All of them are under disruption and they are reaching isolated MOND prediction values. I would say we can actually consider six cases from here itself. 1, 2, 3, 4, 5, 6. Now, all of them, in order to reach the isolated MOND prediction, they have to be undergoing disruption. Now, what is the extent of disruption is the question. So, how do these 6 UDGs that I mentioned here, how do they look? This is how they look. So, I don't even know what's the UDG here, honestly, because I mean, Galfit cannot fit this anymore properly. There are all these are some of them are even beautiful stellar streams after a point. So there is one possible case that looks okay, but still the Sirsic index is 3.5 and 4.5 effective radii. I don't know, I'm not an observer, I don't know if it's realistic. So they have to undergo disruption to reach that level, and when they are disrupting, they look like this. I don't know if observers can even see such objects, which it's a question that I also would like to know. So essentially, before I conclude, now one might ask, what about the far ones, like the 345 megaparsec? Now, the 345 megaparsec simulations at their apocenter, meaning after their pericentric passage, I'm catching them after one pericentric passage. They're not getting disrupted, which is good, but they don't reach the isolated MOND prediction too. They are well below the isolated MOND prediction. So in these cases, surprisingly, their radial velocity is so high that they escape tidal disruption during their first pericentric passage, but they are not disrupted also. So whatever the initial velocity dispersion they start with, they're slightly around that range. They're around that range itself. These are the axis ratios. Nothing very fancy about these axis ratios. They're just in the range that one would expect. and the isolated dispersions also don't go to the isolated MOND regime. Same goes with the Sersic index. Yeah, the maximum is 2, which is I think reliable still. So they don't show any behavior that that looks like isolated MOND prediction. To summarize, due to significant tidal susceptibility, most of the UDGs on high eccentric orbits undergo disruption after one pericentric passage. Low eccentric orbits seems to be, let's say, semi-stable against tides, unless they are too close to the center, like less than 1.2 megaparsec. The velocity dispersion profiles do not reach the isolated MOND prediction. UDGs from far distances escape tidal heating due to high velocities. To summarize all this into one plot, you can see eccentricity and distance, disruption time, the time when they enter disruption, like they've lost 80% of their mass, divided by the initial dynamical time of the cluster. So all the high eccentric orbit simulations, they undergo disruption, and the low eccentric orbits ones, they don't undergo disruption within the simulated time, I would say. Just as my concluding remarks, I would say there are no cases. So the discussion was first infall onto the cluster. Now during the first infall onto the cluster, the galaxies are not disrupted, and I just showed you that galaxies need to be disrupted when they have to reach, if they have to reach the isolated prediction, and they start disruption after one pericentric passage. So we can rule out first infall to the cluster. They have to go through the pericenter and they need to be under disruption. Now heated and disrupted by tides, again this relates to the same point, that they need to go undergo one pericentric passage and then undergo disruption, but their parameters do not match what we observe, what the observations show. So 0 out of 39 cases show this isolated MOND behavior whilst maintaining the realistic parameters like Sersic index, effective radii. Statistically, this is very unlikely, at least 39 simulations statistically. So these two points can be ruled out, in my opinion, from the simulations. How about the other cases? This needs they need further investigation. So thank you for your time, and if you have any questions.
Excellent talk. Right, we have time for some questions. Yeah.
I think you're rather exaggerating when you say that they have to be isolated. This is not what the data show. Even if they are at half the isolated, sigma, it would still be consistent with observations. Because remember, when you say isolated, you took M over L of 1. But if M over L is 2, we already, I mean, you sort of come up with this paradigm that they all agree with the isolated sigma, and that's it. So this is your goal. But that is not true. Okay. If you look at the huge error bars and the possibility of different beta and so on, so even if they are half the isolated, okay, it would still be good. So how many of these 36 models that you tried, let's say, reach half the isolated? Because you have to compare it with the Newtonian, not with that. Okay, if the Newtonian is much smaller, and you still get more, half the isolated, it would still be a rather weak external field effect.
Would you say something like this?
Let me ask, of the 36 models that you try, how many roughly reach, let's say, half the sigma isolated?
So, I mean, we can say it from here on, like, at least 7, 8, 9. They reach half the isolated, but I have to check how they look.
Yeah, but those do not look disrupted.
They disrupt, that's the thing.
But the ones that reach half the isolated.
Yes, this for example.
But the other thought that you show.
The solid lines, they don't reach half the.
Okay, never mind. So the other thing is observationally, okay, as Jonathan mentioned, there are thousands of UDGs. Yes. What is it that, why did people concentrate on those few?
Well,
But there must be selection, right?
yes, there is.
Okay, the selection would probably go in the way of high sigma,
Yes,
right? If the sigma is low, you cannot measure profiles. You cannot.
agreed.
So there is some cautionary.
Definitely. So that's the thing. So on the observational side, there are uncertainties. I will not debate that. But what I'm trying to show is what is the like for the lowest mass.
I understand, but they are atypical. I mean, if you want to compare with your simulations, it is dangerous because even let's say a small fraction of your simulations do give more or less undisrupted appearance, n large sigma. So maybe those are the ones that are selected for the observations. So you cannot say, judge from the statistics of your simulations as far as I can.
So you're hinting at something that only those like sort of unique ones can be visible to observations.
But the thousands that are there, if you will pass the observational criteria.
Okay.
So just one thing regarding the issue of the mass to light ratio. Changing the mass to light ratio by a factor of 2 will only change the isolated MOND prediction by a fourth root of 2. So what you were saying, a better comparison would be if you had an additional line at 1 over the fourth root of 2, which would only be slightly below 1. Right. Now, do we have any other questions?
Not isolated one. Because under external field, they have more or less root of.
Oh, sorry. Okay, fine. Yes, with the EFE dominance, might only be a square root scaling. Yes.
What is exactly your definition of the tidal deformation parameter eta that you use?
Tidal okay, yeah. Susceptibility or
Yeah, the R2 parameter. How do you get that?
so this is calculated from Roche-Loeb. It's calculated from a Lagrangian point of Roche-Loeb, I think, from R1. I don't know that. Maybe Jonathan can comment on it because I've taken this from his article.
Yeah.
I have the calculation, but I don't remember exactly.
I believe it's all comes
It's from
my
your
paper.
paper, exactly.
Yeah,
Zhao.
the definition
Yes.
of 2, I forgot exactly. It's an intermediate value.
I think
Because the Roche-Loeb at 3 can be defined by 3 sizes. It's X size, Y, Z. Z is the
I
strongest.
think Jonathan wrote this paper. And
No, but it's coming from
Zhao.
Hongsheng's paper. So
It's my R2.
yes, it's your argument.
So is this? So there's 3 Lagrange radii. You were saying which direction is
It's
this?
the
No, but-
intermediate. Intermediate. It's a one. It's a so you have it's a as I showed you the Roche-Loeb looks like looks like a American football, yes, and it's the shortest. The longest point is the Lagrange point, okay, and but it's actually more squashed vertically, but there's an in between. Radius, that's called 2, I2, and it has no physical significance other than it is in between. Okay.
But it uses today's.
Instantaneous.
It's today's one now. In the past, if it is tidally susceptible to the sea larger in the past. Let's say that today are half smaller than the tidal radius.
Well, actually,
Doesn't
this is
mean
my
that it was not subject to that.
Which are you using today's value?
No,
Or are you using the distance?
It
Are
should-
you using the pericenter value?
It should ideally be the
No,
pericenter.
so
right?
what I'm calculating, it's actually the surface where the tidal force is equal to the internal gravitational force.
Yeah.
Yeah.
You
And
can do
then
this at anywhere in the orbit. Where
Yes,
you
so
do it.
that defines some, no, but this is calculated on circular orbits.
So is this correct then, that your R2 is calculated assuming the current separation?
Yes.
Right,
Yes,
so
correct.
this could be an important issue, because can you show the graph with the eta values?
Mhm.
Right, so all the eta values could in principle be a lot higher, because typically the way tides are understood is that if the eta calculated at pericenter is above 1, then it would be tidally unstable. right?
Okay.
And you,
Yeah.
well, this is dependent on the scenario. Maybe
No, it's like I set up, I ensure that they are not, I mean, they have not yet gone through the pericenter when
oh,
I
sorry,
set up.
I see. So in your simulation,
Yeah,
this eta is appropriate.
yes, because, yeah.
But in observationally, it's not easy.
You know, I mean, when it goes to pericenter, of course, it will be much higher than 1 because
Okay.
it undergoes
So
disruption severely.
we'll just take one more question if anyone wants to comment on this.
Oliver had a question.
Yeah, I had a question.
Okay. So,
I have to remember the question now. Yeah, very nice work. I was wondering, how difficult is it to go from these simulations to group environments where you, for example, don't have X-rays? So can you set up something like NGC 1052 where this initial discussion about UDGs, stacking dark matter, etc. Came from?
Well, it shouldn't be very difficult. If I know the, I mean, if I can set NGC 1052 as a static potential, and yeah, it should be. If I can set it up as a static potential, launching dwarfs in that potential is not a problem.
So when can you have results?
It depends on my supervisor. So, well, okay.
sorry, we already did a detailed study of dwarf galaxies orbiting DF2 in POR, and that's already published and led by Hossein Hagi, and it shows that the current internal velocity dispersion of Dragonfly 2 is well understood in MOND. So that's already been published.
I was the co-author on that one too.
Right.
Okay.
I think that's it for today's talks in this session by Srikanth. So we'll thank him and